Hello community, so great that you are back. Today we're gonna talk about a new AI model, just 80 million free trainable parameter that will eradicate a GPT-5 system and maybe OpenAI. So let's start. Now, hello and welcome to the channel Discover AI, and we are looking here at the latest AI technology and the latest research. And in part 1, we looked here, hey, for superintelligence, is a neurosymbolic AI really the way to go? Can you trust the neurosymbolic AI for superintelligence? And we find out, what we need in any way for any AI system in the future, we do need massive domain-specific knowledge graph to represent new knowledge to the syntactic GPT systems. And GPT is everything here from a GPT-5 to a Claude system. So, you know what? Let's do this now. Let's build a knowledge graph for a domain and let's have a look at a new technology. Now, luckily for our domain, let's say we take the medical domain, we build a knowledge graph and we encounter in medical already a unified medical language system for AI, which is gorgeous. So we can build a triple for our knowledge graph. And our triple is simple. Now we have a head, the chronic kidney disease. Then we have the relation from the head to the tail. And the relation has a finding site. And then the tail. And the tail is, for the chronic kidney disease, of course, the kidney structure. And this is everything United States edition on. Beautiful, normed. And now we are a little bit mean. Now we say, you know what? We want to trick the system. So we manually create now a sequence that implies now a much weaker connection in our medical domain. And we say, hey, you know what? Maybe we have a triplet of a chronic disease, kidney disease, associated with, so a much weaker link, with a cerebellar gray matter structure. Okay, let's have a look at this. So now they said, okay, let's have a look at the best LLMs on this planet. Let's have a look what we can do, and don't care if it's open source, if it's proprietary, if we have to pay. Let's go with the best models there are. Let's build a knowledge graph with an LLM. So what is the task? The task is, hey, please complete the following medical knowledge graph triple. You have chronic disease, has a finding size, and then I give you here the content, the information, the answer in a text. So no problem at all, yeah? And Gemini 2.5 Pro goes and says, hey, chronic kidney disease has the finding site of cerebellar gray matter. This is the wrong answer. This is the weakest link. This is an error. And I say, okay, it was just Gemini. GPT-5 makes chronic kidney disease has a finding site, cerebellar gray matter. This is again wrong. GPT-5 cannot build from 3 sentences here a knowledge graph. Grok 4, come on, Grok 4. Chronic kidney disease has a finding site, cerebellar gray matter. Grok 4 fails to build a triplet for a knowledge graph from just 3-4 lines of text. But you know, there's one system left. There's one left. And yes, of course, it is Claude Sonnet 4.5. And you know what? Yes, has defined the site kidney. Congratulations, we have it. Just wait a minute. No, wait a minute. Where did the word pediatric came from? This is nowhere in the source text. What is this? Now, if you look closely, you see this is a classic LLM hallucination. This is just something that the LLM hallucinated. And said, you know what? I invent a new term. Great. And now I ask you for a MED-AI, hallucinations. I don't think that they're acceptable in any way or form. So here we come now to the paper of today. Princeton University, and it is an absolute innocent title. Look at this. Efficient and scalable distillation of reliable knowledge graph from unstructured data. Who would ever guess that this is here igniting an AI revolution? GraphMERT, October 10, 2025. And they say, you know, we have here a solution. We build now a graphical multidirectional encoder representation from the transformer architecture. And this is a tiny, tiny little AI system. Not with billions of parameter, but just with 80 million parameter encoder-only transformer architecture. But you know what? We can build a modular neurosymbolic stack. We have in one model the neural learning and the symbolic reasoning integrated in a very clever way. So we have an efficient GraphMERT encoder-only transformer that learns and distills the complex syntactic to semantic abstraction from a high-quality domain-specific text corpus, like archive or bioarchive or meta-archive. And then we have the complete reasoning, where we need a knowledge graph. And we bring it together into one system. So GraphMERT, you might say, this sounds familiar. Yes, of course. Graph, no? This is like I showed you here by Harvard 2-3 months ago. They built a medical LLM, but as I showed you in part 1 of this video, this is not able to find medical solutions. You need to have access to an external object to the LLM, a knowledge graph, where you have here a beautiful representation of all the medical knowledge of this world. And then the problem is how to build here the transfer and everything. And you say, MERT, I know something. Now, 2-3 years ago, we were talking about BERT by Google, and BERT was a bidirectional encoder representation from transformer. What a coincidence. Now, guess what? It is not a coincidence. Because you remember 2 years ago here, in January 23, I did show you this video. And we looked at a complete T5 representation of the transformer architecture by Google. And then we said, you know what? The first half, the encoder part, we call BERT. And the second half, the decoder part, we call GPT. And then something happened. GPT took off. It was amazing. It was a stellar flight. Everybody was talking about GPT. And everybody else almost forgot the BERT system. And now that we hit a wall with our GPT system, that we fail in the logical reasoning of GPT systems, suddenly Princeton comes and says, did we miss something? Did we miss an opportunity? And of course, GPT 3.5 at the time in January 23 was the most important, amazing object here in AI. But at the same time, there was also Roberta, and Roberta was a robustly optimized BERT approach. So they had here mask language modeling, a dynamic. They dropped some complexity. They developed here a very specific tokenizer, byte pair encoder tokenizer. They had large mini badges, and they said, you know what, BERT was completely undertrained. So Roberta was developed. And you know what? Roberta is the base for MERT. Such an old grandpa AI system from January 23 is now the hottest new AI model in town on this planet. Now, if you want to learn about BERT, S-BERT, sentence transformer architecture, if you want to build this here from scratch here, whatever, in a transformer, in a Keras, in a PyTorch, I have 40 videos here on this particular playlist. And you see, 2 years ago, 3 years ago, 4 years ago, I had tons of videos on this, and we built everything on this. And you know what? Princeton now asks, hey, can we do superintelligence without any GPT part of the transformer? Do we need OpenAI? Do we need Anthropic and the models from them? Do we need here the meta models, the llama models? What about we have a different technology that we forgot about? And what about we examine now the options from this forgotten technology? So superintelligence without OpenAI, without Anthropic, without the main companies that carry here the GDP growth of the America dream? Well, it is rather simple, no? You just switch here from the decoder part of the transformer architecture to the encoder part. That's all there is. Encoder, decoder, we have here the next token probability prediction here with GPT-5 and all those models. And now we discover we don't need this. We don't need the complexity, we don't need the model size, and we don't need maybe the compute center for this, because there's another technology available. And Princeton now shows us in this beautiful paper, 70 pages, pure enjoyment, how to encode a knowledge graph now in an encoder part of a transformer architecture. And you know what? Without any GPT system. We don't need OpenAI anymore. We don't need GPT systems anymore. We don't need Claude systems anymore. We don't need Grok systems anymore. there is an 80 million system that is outperforming all those huge LLMs. Isn't this interesting? So our classical BERT and GPT, where GPT mimics the surface level linguistic patterns of a text. And now BERT, where we really can learn and respect the deep semantic and ontological rules of a medical domain. So Princeton did something real clever. Now, if you have a knowledge graph like this, it's simple. No, it's known for quite some times. And now the question is simple. How do you make a graph look like a sentence? So a transformer, but careful. We are talking now about encoder part, like a Roberta, not a GPT, can understand it. So we will now develop a different technology. I mean, Princeton shows us that there's a way. GraphMERT, graphical multidirectional encoder representation from transformers, a very familiar way, no? But something that we never continue to explore its possibilities. And they tell us, if we do this, no, we have here a compact GraphMERT system with just 80 million parameters that completely eliminates the need for pre-training of large unverified text, making the approach much more practical than employing here expensive LLMs like GPT or Claude or Grok with billions or trillions of parameters. And this is what I call an AI revolution. And it can be scaled and provided with more data. If you want to combine, let's say here, the 80 million for the pure medical domain with a pharmacological domain knowledge. And then you need a little bit more of extra compute resources. Yeah, for an 80 million model, not a billion model. And they said, we do this. Princeton said, come on, let's do this. Let's have fun. We train GraphMERT now with 12 hidden layers in a Roberta architecture with 8 attention head with a hidden size of 512 and an intermediate size of a fully connected layer of 2K, totaling therefore to 79.7 million trainable parameters. We use here specific tokenizers, the BioMERT BERT tokenizers that was especially trained on biomedical text, trained on a vast demand of the medical vocabulary, beautiful, and the tokenizer size is relatively small with 30K. So our vocabulary size is not that huge that we would expect. So let's build this. Hey, wait a minute. So if we build this, we need a training data set. No, this is a BERT system. I mean a MERT system. I mean a GraphMERT system. No? So let's do this here on a subdomain like diabetes. Diabetes research is really important currently in the US and globally. So let's build a training data set for our MERT system. So what we need? What we have medical papers, unbelievable. No? Medline journals, whatever you have, 350,000 abstracts for training and 40,000 abstracts for evaluating. So we have hundreds of millions of tokens of pure textual description in medical technological papers. Great. And then they said, let's make it easy. If we have the starting condition for this system, we want to have a nucleus where everything is starting from. No? So they said, let's build a seed knowledge graph, a little tiny knowledge graph that is here the original core from everything else will develop from this seed knowledge graph. And of course, you take the UMLS, method thesaurus and everything, and beautiful. And you have here clinical documentation of molecular biology and the data exchange, and great. So, and then they said, okay, so we have the syntactic and the semantic sources. Ne? And from the syntactic data sources, these are our scientific papers, the textual papers. What we need to do now is, let's just find the entities, the medical entities. They call it the head discovery. No? Now, unfortunately, they said, you know what? We have an LLM for this ready, in the shelf. Why should we build something? So we take here an LLM, which turns out to be, well, not really the best idea because we want to break loose from LLMs, but okay. They said, just for the discovery, not for the reasoning, just for the discovery of the main technical terms in medicine, we use a QN332B model. No? Asking it to search for medical entities that are now relevant for diabetes or whatever. Now, you could go to a medical database and just extract it, but it's, you see, it's so comfortable just to use an AI system. Okay. And then I said, as I told you, we need a seed knowledge graph, a small expert-curated set. Maybe you can do this with a human-curated set. This would be perfect. So you do have a ground truth knowledge graph, and you build on this, and you let it grow. And you have your typical triplets, your head, your relation, your tail entities, and you have just to provide the initial, the starting point, the semantic examples, and the ontological constraints. And they said, okay, we don't went with a full primary knowledge graph in medicine or diabetes, but we just took here from, whatever the literature is, 28K triplets in the diabetes case. This is available, so let's take it. Great. So what do you have? They have the syntactic data sources. These are, 100,000 preprints here in the MET domain. All the beautiful papers that were published in the last 2-3 years on whatever topic. And you discover the entities, the medical terms. And then you want to have the semantic data structure. So you start here and you say, okay, similarity matching with the text. You have the triplets, you develop here the match triplets, you can inject this, and then you come here to a seed knowledge graph. Now this seed knowledge graph has a very particular format. They call it here Leafy chain graphs. So let me explain what it is and why we do it. What we already can see here is from the text here on diabetes research, the textual discovery here of the entities, you see here in orange, so the technical terms here are here on our graph. And then if you have here the different tails to a technical term, they have here in whatever, let's call it blue, and you have relations to this, interestingly. So again, let's come back. How do you make a knowledge graph? If we start now with a seed knowledge graph, so this is the nucleus where everything condenses upon and builds up. So how can we make this look like a sentence for a transformer? But careful, not a GPT transformer, but an encoder transformer like Roberta. We don't need any GPT in this. So, as I told you, the Leafy chain graph encoding, a new methodology invented by Princeton, or maybe further developed by Princeton, is now an elegant answer. What they do from the methodological point of view, they just flatten it. They flatten both the syntactic information, this means the how to build from words a sentence information, and the semantic information, this is simply the knowledge graph triplets, the semantic, into a single unified sequential format that the transformer, again the encoder part, the Roberta part, can process. Simple, no? You just have to have the idea. So just to be sure, no? Bidirectional context is essential here. Our BERT system is here the one that outperforms a GPT decode-only system. Because a GPT system can only look at the past tokens, but you want a system that can look at both tokens in both directions and in multiple directions to see every other token in the input sequence simultaneously. And of course, think back 3 years, well, how we did this with BERT, we have mask elements, mask tail, and the model needs to understand the full context of the head entity and then predict here the mask tails. We solved these problems 3-5 years ago, and now we just apply it here again in a little bit more complex structure. So the Leafy chain graph has a distinct backbone. This is the chain itself, the chain of the root nodes, or embedded now in the syntactic space. And the branches, those are the leaf nodes, and they are embedded in the semantic space. And now guess what? This Leafy chain graph has now a crucial connection of grafting a triple onto the graph and combining both mathematical spaces. So here we see it in a flowchart. So again, we have the semantic source, our seed knowledge graph with our triple that a human maybe had as an original starting point. And then we had all the 100,000 medical papers that exist somewhere in the world. And you see we identified here the main medical terms for diabetes research. Those are here are orange, and now we want, and just pad it. That's it. And so from the seed knowledge graph, from the triplets, we know our tail structures now, and we have the relations. So now we combine those, we build our chain graphs that have now the syntactic information and the semantic information combined. And we train now with a training data set the GraphMERT system in more or less the same way we trained our BERT systems. And if we have it trained, guess what? We use this AI system to predict the future, to predict new research, to predict new complexities, to predict new patterns that can emerge here, to predict new triplets. And now again, unfortunately, they went back here and said, we just need an LLM as a helper to help us sort this. And then we have a new extended, extracted knowledge graph with all the knowledge here from our papers here now in the knowledge graph. So we build up the knowledge graph. This is beautiful. This is beautiful. Unfortunately, again, they went with an LLM. Let's have a look at this in a little bit more detail. Yeah? So we have all, let's say, the PubMed papers, not the training data set. So you have the sequences, all the leaves are empty. You start here only with your primary medical term for diabetes, yeah? In orange. You choose your head for the triple to be predicted. And then you have here a sequence with one mask leaf. You just mask like in BERT, you're familiar with this. And then you predicted the mask leaf tokens, the top K, the top 5, the top 10, with the trained GraphMERT model. And then you get the top K tokens here for the tail. Those are the tail token candidates. I don't know, whatever the medical terms are. And then you just have it. So you build up your knowledge graph with new knowledge. Now, interestingly, when they designed here the GraphMERT pipeline, so you have now a sequence where I say, okay, diabetes has the finding site and the tail element is open. And you have now text from the papers. Now, and here you have this particular text. Never mind. This was chosen here for a particular reason. So what you do, wait a minute. So what you do, you have here, as we just went through here, to train GraphMERT system. Unfortunately, you have here a helper. This is not a reasoning LLM. This is not a thinking LLM. This LLM is just helping here auxiliary second important data. And we could substitute this LLM completely gone. But it is in the paper because it is, simple and nice, off the shelf, great. And then we have here a sequence with a triplet and another sequence with a triple. And what we do here, the system just evaluates now the similarity score, cosine similarity in the vector space, exactly, between the triplets from the previous step and the sequence of the origin. And only triplets with a score higher than a particular threshold will pass. So we have here another filter established, and then we have our output. And the output is, like what we expected here, the diabetes has the finding site endocrine system. Now, if you don't do this here with a GraphMERT system, and the authors here showed us, hey, what I built with an LLM, now the knowledge graph pipeline without GraphMERT, but just LLM and knowledge graph, the classical way, you know what we find? We find that the solution by this system is diabetes has the finding site urban area. Yes, an urban area was in the primary text given here. What a coincidence. It is an experiment exactly done for this. But you understand what happened? The LLM, the GPT system, misinterpreted has a finding site relation, treating here the token site as a geographic location, and thereby referring now to urban area as a site, instead of an anatomical structure here which results in an invalid triplet. It is violating here the ontology of MET. You see, this is the difference now between the old system and the new system. And they have a lot of additional explanation in those 70 pages. They have a ton of experimental data, but you need 2 days to really have a look at this paper. Okay, now GraphMERT, you know, in a transformer layer, we have an embedding layer, and then we have our transformer layer. So the very first embedding layer is now also specific. No? Not only for the transformer layer, we have to have here some fused nodes with some scaling that depends on the distance in our vector space, but we have also in the embedding layer, we have now to combine the syntactic space and the semantic space into a common space. And the question is, hey, does a common space exist at all on a mathematical level? No? So what we have now is an attention mechanism. And here, of course, a graphical attention mechanism, a hierarchical graphical attention mechanism that encodes now our semantic triples in the knowledge graph. And they are leaves connected to a root nodes. No? And now this attention mechanism on the graph uses now the leaves, the relations, and the head embeddings, resulting now in a new updated fused node feature. So in the attention layers, the attention weights are now multiplied here in the transform architecture here, in the layers here, by a function that exponentially decreases with the pairwise distance. And they encode here the graph relations and the graph distance respectively. This is absolutely similar what you know here from a RAG system, from a vector space interpretation here of a cosine similarity, where you have closeness, absolute environments, equaling semantic similarity. But this is here not advanced level. This hierarchical graph attention mechanism is a key feature in GraphMERT for the training in general. So for each injected triplet here, our HGAT performs a relation-aware attention to encode the full triplet semantics into the leaf embeddings, thereby, of course, replacing the initial leaf token embeddings. So we update here our relations. We update the integration of new knowledge into the knowledge graph. And this occurs in the input embedding layer before the transformer processing, enabling therefore backpropagation to the relations during the mask node modeling that we know from BERT. And this happens layer by layer in a hierarchical structure, therefore the name, hierarchical graph attention, to make sure the model captures here the bigger picture of how facts connect now. New knowledge is built and integrated with the old knowledge, quotation mark, which helps avoid mistakes and build a reliable knowledge graph you can trust, because you can immediately find what was the original sentence and you hope that there are no hallucination at all. And here you have the complete flowchart. This is not a flowchart. So we start with a training data set for our GraphMERT system. We have now, unfortunately, with an LLM here, that the technical terms are discovered here, the entity discovery within an LLM. Then we have a similarity matching, and we have to have a seed knowledge graph. So we have here the papers and the seed knowledge graph. Those are our input data, if you want. And then we have here the training of this beautiful new GraphMERT system, the encoder only part of a transform architecture. Now this now can, if it's trained, predict your details with GraphMERT, combine the tails token, unfortunately, again with another LLM, because it was convenient just to take an LLM and not to find a better solution without an LLM. We have a similarity check, embedding based, and we have now an expanded, added, grown knowledge graph with more knowledge. This is it. Now you see the authors did use helper LLMs, not reasoning LLMs. No, just helper LLMs for 3 auxiliary tasks. First, as I told you, discovering the head entities. Second, selecting the relations for subsequent GraphMERT predictions. And combining single token prediction into nice sentences, into meaningful relation-aware tail phrases. Into GPT just is building nice sentences that humans understand. But there's no logic in it. So let's have a look at the mathematical spaces. And I know you have been waiting for this. Of course, me too. So we do have here from GraphMERT the backbone. This is here the chain of the root nodes. And this is here from the research paper, from medical, from MedPub, or whatever you have. This is the syntactic space itself. We broke it down into individual token. A token becomes a root node in the chain. And this part of the graph represents here the pure syntactic space. It holds the original unstructured text, providing here the grammatical and the contextual foundation of any knowledge that will be extracted. Now, in the paper, they've chosen here a specific number. So each input sequence is standardized to have a fixed number of root nodes, 128 tokens. They chosen, this is it. Okay. And if a sentence is shortened, it's just padded here with the pad tokens. And if it's longer, it is truncated or split. Standard BERT. So let's have an example. The sentence, metformin treats type 2 diabetes, has become now a chain of root nodes. Metformin treats type 2 diabetes, our token structures. Then we have the branches, the leaves. Now, just to make clear, the leaves live in a different mathematical space, in the semantic space. Each root node in the chain has a fixed number of leaf nodes attached to it. They decided to go with 7. Just chosen. This is it. You can choose 15. Think of them as dedicated slots or containers of holding semantic information to this specific root. So the leaves represent now the semantic space. This is where the tail entities of the knowledge graph triplets are placed. And in the paper, each of the 128 root nodes has chosen 7 leaf nodes. This was enough for a simple diabetes medical domain. So this creates now a large regular grid of 896 leaf tokens. And during the training, of course, most of those leaves are empty or filled with a pad token. And only the leaves corresponding to a head entity in a known triplet are populated. So you could argue, well, this is a sparse graph. Yeah, but it is a beautiful graph. There is no hallucination yet, except where we use 3 times the LLMs, but more about this later. And now the crucial connection, guess what? We bring it together. Grafting your triplet onto the graph. So the head entity is the span of a text found within the sentence, therefore already exists in one or more root nodes. Let's say metformin is the first root node. This grounds the semantic fact directly to its textual origin. We know exactly where this information came from which original paper, medical paper. The tail entity is placed onto the leaf nodes that are directly connected to the head's root nodes. For example, the token type 2 diabetes would be placed into one of the 7 leaves associated with the metformin root node. And the relation acts as the type of connection or the edge attribute that we know from graph theoretical mathematical physics. Let's have an example. Chronic kidney disease is a renal disorder. The C triplet is chronic kidney disease has a finding site, kidney structure. So what are the root nodes here? Chronic kidney disease, CKD, is a renal disorder. The 7 leaves for the root node chronic, the first one here, become kidney structure, pad. Clear, no? The relation has a finding site is now implicitly defined by the connection between the head span, chronic kidney disease, and the tail span, kidney structure. And this connection will be implicitly modeled and trained during the training by H-gate, by this attention mechanism for the graphical system. So the final flattened sequence, and we did all of this because we wanted to have a flattened sequence as an input to our encoder transformer blocks, looks something like this. Chronic disease, disorder, kidney structure, pad. So this is exactly 128 root tokens followed by 128 times 7 leaf tokens. So we have a flattened representation where a known transformer architecture can work with this. It turns out, Princeton tells us, hey, this is effective. Why? Why is this encoding so effective? It enables the adjoint mask language and mask node modeling training. So the model can be trained to predict the mask tokens in the root chain, thereby learning the syntax, and the mask tokens in the leaf space, thereby learning the semantics at the same time in the same model. How beautiful is this? Of course, it creates a pathway for the gradient flow to the relations, and during the training, yes, beautiful, you know this. So here we have another example now, a screenshot from the paper, and I just want to give you here a feeling for this. So we have a sequence, a text sequence 1. Authors, yes, it's about non-alcoholic fatty liver disease, beautiful. And yes, and this is it. The pathopsychological pathways. What is the head? This one. What is the relation? Is a, plays a role, has disposition, cause of, associated with. And now the top 20, you remember the top K, the top 20 GraphMERT predicted tokens. And here you see this. So for each is a plays role relation, you have now the predicted top 20 tokens. This is based absolutely on the new knowledge graph. So if you want to see this now into triplet structure, the head, you have here the head, you have here the specific relation it was trained on, and this is now the tail it provides, formed from the GraphMERT predicted tokens. Now, just to make this clear, the mathematical complexity is not trivial. We are working with different mathematical spaces now. We have a syntactic space, This is more or less, if you want, what our GPT did for us, but we have now this in our model. So we have to integrate the syntactic space with the semantic space. So a vector space for grammar and context, like GPT training was, all of the internet, to learn the grammar and to learn the context. And then we have the semantic space. This is the knowledge graph. This is the real given structure and dependencies of our technical terms in medicine. This is a vector space for meaning and facts. And yeah, if you want, an ontology is a formal specification of the terms and the relations in a specific domain. We have medicine and we have diabetes as a subdomain. So let's have a look at the syntactic space. When we say syntactic space, we are conceptually referring to a domain of a language structure, grammar, specific word order, parts of a speech, and the contextual relationship between the words in a sentence. This is exactly syntactic, how a sentence is built. The mathematical representation in GraphMERT, this concept is given a concrete mathematical form, a high-dimensional vector space in the simplest form, or you can go to a vector representation populated by the embeddings of the root nodes. The tokens, remember, from the original text, from the original Matpub papers. So every token in the source sentence, like metformin treats disease, is now mapped to a vector, a 512-dimensional vector in our Roberta architecture. And the model's encoder, not decoder, the encoder layers are now trained via the masked language modeling, a specific loss function that you know from BERT, to manipulate these vectors based on their context. This is why context engineering is now so, everybody's talking about it. The result is that words with a similar grammatical function or a contextual role will have vectors that are now close by an absolute environment in this space. For example, the vector for the word treats and manages would likely appear near each other because they are both transitive verbs that often appear between a drug and a disease. Second space is the semantic space, the vector space for meaning and facts. So it's such a beautiful space, refers to the domain of meaning, concepts, factual relationships. It is about what things are and how they relate to each other ontologically in this domain. For example, it captures here the fact that diabetes is a disease and metformin is a drug used to treat it. So this is now maybe the same high-dimensional vector space, maybe it's a different, but it is now populated by the embeddings of the leaf node, the tokens that form here the tail of the knowledge graph triplets. And this space is specifically structured by the masked node modeling loss and the H-gate module. So this training forces here the vector in the semantic space to align based on the factual ontological relationship of the domain, not the word occurrences like we had in GPT. And this is the beauty. The critical insight, if you want now from this paper by Princeton, is let's build a common shared space out of these two subspaces. So the syntactic, the root space, and the semantic, the leaf space, you can build them that they are not separate spaces. Maybe you can build them that they are just two different views or two different sub-regions, sub-complexity regions of the same unified high-dimensional, much more higher-dimensional embedding space. This is here about complexity theorem and mathematics. This is something really beautiful, but not part of my video here. So again, the syntactic training, the masked language model arranges here, let's say, the cities, these are the tokens, on a map based on the road network. How you can travel from one city to another with the correct grammar. The masked node modeling for the semantic training rearranges the city now on the same map but based on their functions. Like you group all capital cities together, or all industrial cities, or all coal cities. So you see, we built here those new systems here in the same space. And now you hope that the output of GraphMERT is now the perfect knowledge graph. Added new knowledge, build up new knowledge, integrated the very latest knowledge data. And solution A is simple, no? You use a graph query language, Sparkle or Cypher, like running SQL query on a traditional database. There's no ambiguity, there's no hallucination. It is just pure cold logic. And this is what you need in medicine, this is what you need in finance, this is what you need in theoretical physics and in quantum mechanics. The graph database will execute any query and return a list of drugs like metformin or whatever with a mathematical certainty. This is impossible to do with a standard LLM because a standard LLM, like a GPT system, is just a statistical pattern. And then, of course, you have the solution B, and now it gets interesting, GraphRAG. Remember? Now, what's interesting is that the authors use GraphRAG to validate here the GraphMERT architecture. Show you this in a minute. But GraphRAG, doctor asks in a natural language, hey, what are the treatment options for a patient with diabetes who is also obese, to the AI system? And then this AI is retrieving now from a reliable knowledge graph. It first queries here your GraphMERT generated knowledge graph to find here the relevant facts, the sub-networks here, small local subgraphs of the verified triplet. 1, 2, 3, 4, beautiful. And then it just augments you the prompt. You have in-context learning, you have few-shot example. Prompt looks something like this. You have the system prompt. Hey, you're a helpful medical assistant using only the following facts. Answer the user's questions. Facts are 1, 2, 3, 4. And the user question is, what are the treatment options? Now you see here the LLM now generates an answer, but its creativity is, I wouldn't say really completely, but 90% completely constrained. It is forced to reason over those 4 provided facts, hopefully. But of course, it can hallucinate at any time in an amount that is undefined. But it is hopeful reducing the hallucination with our knowledge graph integration. Okay, let's come to a summary. I know what you say. Hey, where are the training algorithms? How do I code here this? What are here the unifying objective if we build together spaces? Look, it is so simple. You have a dual objective that distills here the syntactic patterns into the semantic prediction, learning here the global relations across here the complete text corpus. It is simple, but this is just the beginning. Yeah, results. We have to look, hey, is this thing working? Or was this just an idea? So here we have the FActScore knowledge graph evaluation in percentage points, and there's a whole definition and pages in the original paper. I just give you the result. If you build a knowledge graph with an LLM, your percentage point, your performance is 40% for the context and 48% for context and the general truth as defined in the paper. Now, if you have this new GraphMERT system, the context only jumps from 40% close to 70% and from 48 to 72%. So if you build a knowledge graph with an LLM or a GPT system or with the GraphMERT system, there's really a difference. Look at this, 40 to 70%. Now, of course, you might ask, hey, but why are those LLM knowledge graph fact scores are so low? And Princeton looked at this, and there's a complete here analysis. And they said the LLM knowledge graph scores poorly performed when validated here on the QRN332B, which flags here its own error. And this underscores here the weak prompt's durability. Knowledge may exist in the parameters, yet the prompt-based generation fails to elicit correct ontology respecting triplets. This is what I started the video with this beautiful example. GPT-5 fails, Grok 4 fails, Gemini fails. This is what we see now. And they even did a further analysis and they found 3 facts. The knowledge graph built by an LLM, by a GPT system, has a relation misinterpretation. The GPT model mapped the relation by lexical similarity rather than, in our domain, ontological meaning, drawing only from its internal knowledge and not from the given facts. Second, you have a systemic malformed repetition. The same ill-formed triplets reappear across different text chunks. An overlinking a head-tail pair, multiple largely invalid relations in our knowledge graph are assigned to the same entity pair. So now we understand why we cannot build knowledge graph with LLMs that are based on GPT systems on the decoder part of a transform architecture. And now I know what you think. You say, okay, this was the Q1, but let's go to the best model. Maybe we have GPT-5 syncing max full power. Let's do this. Let's go for the most expensive, best good-looking model, GPT-5, full syncing. And you know what? Look at this. On the left side, you have here the performance here, 100% for GraphMERT. Never mind what it is in detail. You have this over pages and pages in the original paper and GPT-5 syncing. Look at this. Now, absolutely equal performance. This is great. But unfortunately, Princeton put this in the first place to show us, if we compare this to additional medical terms, it looks like this. So you always see here the left indicator is here the GraphMERT system, and the right indicator here of this bulk is here GPT-5 max syncing mode. Green is what we want, orange is maybe, and the red is failure. So here on the term metaphor mean, the GraphMERT system achieved here, if you want here, I don't know, 95% of yes and maybe, but GPT-5 syncing achieved something below 40%. So there's a massive difference. But it doesn't mean that statistically you can get lucky with one term, like this term here, but on all the other terms, GPT-5 syncing fails to build here the knowledge graph. Now, if you look at this, you say, okay, here, let's hit this 80% performance. This is 85% performance, 90% performance, 95% performance. Why is this not 100%? Why is GraphMERT not 100%? Why is GraphMERT not better than 90%? And here, a quote by the authors here, by Princeton. The main issue in the GraphMERT triplets are vagueness and incomplete tails. And you say, how is this possible? And then it turns out the tail incompleteness arises when the helper LLM, the GPT, that we have to have as an auxiliary AI system, the helper LLM accepts here an incomplete token as a valid tail during the token combination. And I say, it doesn't matter what helper LLM we tested, it's always the same. All the LLMs hallucinate. As I showed you at the very beginning of this video here, when we had our triplet. Why GraphMERT is not better? Because unfortunately, we still have those 3 times their LLM that are not reasoning, but are just helping to filter out things. And they have now that they have incomplete token as a valid tail token. So we know where their error comes from. What are the insights? I think GraphMERT's success is based on a complete novel approach. It really enforces here an ontological alignment in the medical domain during the training and the extraction process. And this is a good thing. And instead, the old way with an LLM, with a GPT system it was just guessing. It was calculating statistical fluctuation and probability densities, the next token prediction, based on a surface level word correlations from their training data. But now GraphMERT learns semantic relations embeddings that adhere to the strict rules of a professional graded ontology. And this is the beauty now of the system. And you see what? We don't need a GPT system at all for the next generation of AI. And you might ask, do we need OpenAI at all? Do we need, I don't know, perplexity, anthropic models at all? Or do we just discover a new technology that would allow us to build just 80 million free trainable parameter models, and we don't even need the complex data infrastructure from NVIDIA? Isn't this beautiful what new technology can, maybe, hopefully, theoretically achieve? And I think this is just the beginning. So if you're interested, hey, why not subscribe? Or maybe even join and become a member of my channel. And I hope to see you in my next video.